Applying the calculus we have so far to projectile motion, there are a few definitions we have. The first is that velocity is the derivative of the position function with respect to time. So you can think of this just like you did in one variable calculus, that the v is r prime. And acceleration is the derivative of the velocity with respect to time. So acceleration is v prime. And also related to velocity, we have the notion of speed. Now speed is just the magnitude of the velocity. So we want to get rid of any sort of direction. Just look at the magnitude. So the speed is the magnitude or the norm of the velocity. Or if you wanted to write this in terms of r, it's the norm of r prime. Let's look at an example of this. Let's say we have a particle moving along a circle. The circle is radius a, and it's moving along with some angular speed omega. So it's got position a cosine omega t, a sine omega t. So this is our position function. So if we were to just sketch this out, we have the circle of radius a, and this is really moving along in this direction with angular speed. So the change in this angle, this angular speed here, is omega. So let's go through and get the velocity. The velocity of this is the derivative. So this is negative a omega sine omega t and a omega cosine omega t. And if we were to look at the speed on this, so the speed is the magnitude of this. Before we do this, these two components both have an a omega in common. So we can actually factor out the a omega and then take the norm of negative sine omega t, cosine omega t. So now if we're taking the norm of this a omega can just come right out of the norm. And then we're going to take the square root of the sum of the squares of the components. So this gives us sine squared omega t plus cosine squared omega t. And then we can use the Pythagorean identity. Sine squared plus cosine squared is 1. So the speed is just a omega, the radius times the angular speed. Now let's go and get acceleration. So the acceleration on this is we take the derivative of the velocity. So we've got now negative a omega squared cosine omega t and negative a omega squared sine omega t. So these we can see both have a negative a omega squared, and then what we're left over with is cosine omega t, sine omega t. If you look at this right here is just negative omega squared times the original. So this is negative omega squared times the original r. So what that says is, if we were to sketch out on this picture, we know that the position function is given by this point. Let's not make it on this. Let's make it sort of on the corner of this area right here. So our position is along this angle right here. There's our position function. The velocity we can see is moving along in this direction, and our acceleration is pointing in the opposite direction. If our position is pointing outward, the acceleration is pointing inward. So the acceleration is running parallel to the position function, although it's in the opposite direction. So we have the position function is out here. The velocity is pointing along the direction of the circle, and then pointing back toward the center is the acceleration. So that's the derivative formulas applied to projectile motion.